So what I'm doing here is I'm going to introduce some radioactive material into an ionisation chamber. And the way that I do that is to just open this tube here, which...
Oh, it's on the board!
Yep, there we go. I just open this tube here and then I'm going to pump it about 3 times. You'll see the balloon inflate, but it is perfectly safe. Even if the material were to come out into the room, it would be perfectly safe. Now what I'm doing is I'm pumping air through the radioactive material, and what we should find is that as a result, the radioactive material, we have a much higher current because the electricity can now travel through. Now what we're going to do is we're going to record the current and the time. So the current is just about at its peak now. We're recording it, it's still going up a little bit, it's starting to go back down, and what we'll do is we'll record as it goes back down. Hasn't quite peaked yet. We'll record as it goes back down against time.
It's peaked.
And you can see there is the random nature to it as well. You've got the occasional bit going back up, going back down. But over the next few minutes, it's going to drop, and it should take about a minute to drop halfway. Yeah, I think it's a bit over a minute. I think it's about 1.5 minutes on this one. But this will enable us to pull out the data. You can see it's dropping much faster now. And it's dropping fast because there's quite a lot of it. So we're in that part of the exponential curve where it's dropping really quite rapidly. And then it will gradually slow down. And we should find that it drops at about the same rate. So that we get a rate that's proportional to the amount of it that we've got. Now, I don't want to worry anybody, but I'm sure you've seen the film Spider-Man. There is actually a spider next to the radioactive source at the moment. It's quite funny. But you can see now the rate is slowing down. It's still going down, but it's going down more slowly. And we've passed the halfway point, so we've got 1 half-life's data, but I would like to get 3 if we can do. Now, although I'm not using a Geiger counter, the current is proportional to the amount of radiation that I've got, so it's as good as having a Geiger counter, really. So we are getting down towards a quarter. So 2 half-lives, we're coming up to 2 half-lives. But if you can get 3, it's always a good idea to get 3 if you can. So I'm going to try and get it down to about 2. And then what we can do is we can pull out the data every, tend to do every 30 seconds. We might do every 20 seconds to get enough data. You can see it's gone back up a little bit. That's perfectly normal. And the lower it gets, the more that randomness becomes visible. Sorry? Yeah, I was just making sure it was showing up okay on the screen as well, but thank you.
Why so would it go up? Because surely when it decays, there's no way it can...
No, but there's always random emission going on anyway. So the overall trend will be downwards, but the closer we get to 0, the more the randomness shows up. Radioactive decay, in terms of the exponential, is a model for large numbers, not for small.
But why? But I don't see why the kind of the current would go up
because there's some random emissions going on anyway. There's always random emissions of radiation anyway.
Oh,
or it might be a cosmic ray passing through our sensor or something like that, but there's always going to be random emissions, but they are much, much lower. So I'll leave that going until 10 minutes, but I think at the moment we're pretty much down to random emission, but we've got enough data there for to be able to see at least 3 half-lives going on, which is great. Now the second experiment we'll do in a minute with the protactinium, because the radiation levels are much lower, it's much harder to get a decent result, but we will try. The PAG requires you to have done one or the other, but it's quite good to have done both. In the exam, you might get some questions on how do you handle radioactive material. Well, the main thing is to make sure that you are never pointing it directly at someone, and obviously that there's no contamination of a surface or a person. So if the radioactive source gets broken, you need to make sure that no part of it ends up under somebody's fingernail or anything like that. Because it's when you're exposed to radioactive material for a long time that the danger really creeps in. None of the sources that we've got are particularly high level. Okay, so I'm going to